So, hi all, thank you for coming. My name is Mario Fusco. I'm from Italy and from Red Hat. I work mostly on Drules, which is the rule engine of Red Hat. I'm occasionally also collaborate to Quarkus, and yeah, I'm doing some more work on Quarkus these days because we are trying to integrate Project Loom virtual threads, and that's why I started mostly experimenting with them. Okay, so uh, let's figure out how we arrived here, why we are speaking about virtual threads. So, as you all know, in Java, you mostly have what we call just threads, but they are native threads, meaning that they are threads that are borrowed by the operating system. And what Java does is just creating a very thin wrapper around them. So basically, you are using in Java the threads of the that are provided by the operating system, and this means that they are a scarce resource. They are a costly resource in terms of a memory footprint mostly, and this implies that you cannot have many of them. Okay, so what Project Loom does with virtual thread is getting rid of this constraint of this one-to-one relationship between operating system thread and Java thread, meaning that the operating system thread now are basically used as a carrier for many virtual threads. So in essence, many different virtual thread can be multiplexed on the same operating system thread. Okay, and the other characteristic of virtual thread, and the main reason why you may want them, is that they can uh, go to sleep gracefully when there is a blocking operation. When they need to wait, they can be removed from the carrier thread. So at that point, another virtual thread can take their place and do something useful while the other virtual thread is waiting. And then when the blocking operation is terminated, the virtual thread is waking up and can be reallocated on the carrier. That cannot be the same carrier. I mean, it can be very likely, and we will see this in more details later. Very likely, the carrier thread where the virtual thread will be waken up, will be reallocated, is different from the one when it went to sleep. So a few numbers just to give you an idea of the difference in weight between native and virtual thread. What happens with native thread is that you have around 2 kilobytes of metadata, while with virtual thread they are only around 2 to 300 bytes of data metadata. But in reality, this is of course not the main difference. The main difference is that with native thread, you need to pre-allocate at least 1 megabytes, probably closer to 2 megabytes of memory just for the stack, regardless if you use or not. Okay, so you need to pre-allocate the stack, and this is the area of the memory that will be used for the stack of that thread. If the thread has 3 calls on the stack or 3000, doesn't matter, you are consuming that resource. Okay, well, while with virtual thread you have a more pay-as-you-go model. In this case, the stack is just a data structure. Is in reality is just a data structure on the heap. So as any other data structure in the heap can enlarge and shrink, and when you don't need a very deep stack, you are deallocating the calls on the top of the stack, and that calls are again just like a linked list, just like a data structure on the heap that can be claimed by the garbage collector and reused for other stuff. So this is the main difference about the memory footprint between the native and virtual thread. And the other very relevant thing is that what typically happens when you do a context switch in native thread, you do this in kernel space. You are switching between two threads of the operating system, so you do this in kernel space. Context switching for virtual threads happens in user space, and this is another very relevant things for performance, as we will see later. Okay, so given all this list of features, the main claim that they made when they started advertising virtual thread is that, wow, you can now create millions of threads on your Java virtual machine, right? And when I heard this claim for the very first time, I was a bit skeptical. I mean, do you really want this? And I remember a few years ago, I gave a talk at DevOps UK when I compared the different concurrency model on the JVM. And what I said during the talk about multi-threaded application is that normally you design them like this, okay? But in reality, what happened is that. So, I mean, yes, puppies are nice, but you probably don't want millions of puppies like this around on your JVM. And so this is why I was a little skeptical about the claim. Now you can have millions of threads, right? And yeah, in reality, yes, cool, you can create millions of them, but really nobody cares. The fact is that, yeah, it's true that you can have millions of them, but this is just let's say a side effect of the design, of how they are designed and how they behave. Okay. The fact is that let's figure out why you really want virtual thread. You really want virtual thread because, again, you don't want to consume a scarce resource, to waste a scarce resource on a blocking operation while the native thread is not making any progress. The thread is blocked, but it's a scarce reason, and no other can use that same thread. Okay, so we work around this problem with reactive programming, meaning that, well, probably some of you have done some reactive programming. Yes, and you know, it's nice, but it's also a little painful. It's hard to write. It's really harder to me to read. It's really hard to debug, to figure out what's going on. When you have a stack, you also have a truncated stack and you really don't know where that call comes from. So it is a solution, but that comes with some problem. Okay, so what you may want to do is having the same feature, meaning not waste a scarce resource on a blocking operation, but in a way that looks synchronous. And this is what virtual threads are really good for. They are really good for waiting. They're really good for waiting without in a non-wasteful way. Okay, without waste any scarce resource of your Java virtual machine. Okay, so in essence, when I first approached virtual thread, my feeling was, yes, they are not really enabling something that was impossible before. Again, it is really possible with reactive programming, but they allow to do this in a much nicer way, at least under a syntactical point of view, because you don't have all those callbacks and function composition that you need with reactive programming, but you can write your program in a way, again, that looks synchronous, but in reality it is. So my idea at time was that, okay, so let's make this analogy. We can say that Loom is for concurrent programming, what Lambda has been for functional programming, meaning that you can do this with Lambdas, with functional programming. We can have a person or a stream of person, and we can filter them with the initial of the name, and then we can aggregate their ages, okay? And do we need Lambda to do this stuff? Well, if you think about it, in reality, no. You can write exactly the same thing with anonymous inner class, but probably you don't want to write this kind of code, right? So my idea was, okay, so let's say that Loom, that virtual thread, is syntactic sugar for asynchronous programming. In the same way, like lambdas expression are syntactic sugar in this case for anonymous inner class, and then making the functional programming in Java more nicer to read and write. Okay, and of course, since I like to be very vocal on Twitter, I wrote this thing on Twitter, and I had a very nice discussion. Well, in reality, Twitter is not the best media to do this, but for some reason, I always end up making this discussion on Twitter. So, Ron Plessler, which is the project lead of Loom, made me notice that yes, what I was saying was true, but was only half of the story. And the second half of the story, probably the more challenging for the team who is working on Project Loom, is working on observability, and is working on the fact that yes, you use this abstraction, you use virtual thread, but in a way that is totally transparent to user. So they created this abstraction on top of thread, which are virtual thread that do all this machinery of having a stack modeled as an object on the heap, and switching out when there is a blocking call, and all these things are totally transparent to user, okay? And of course, you have all the monitoring system that you were used to use with native thread. They work exactly in the same way for virtual thread, okay? And this was a very great achievement indeed. And yes, so as I said, this could have been a really nice blog post. For some reason, it's a messed up thread on Twitter, but it is what it is. Okay, so these are the features of virtual thread. Of course, virtual thread are one more tool in our toolbox, okay? This is very important. Virtual threads are not going to entirely replacing native thread. I'm not saying from this version X of future version X of Java, you will no longer have native thread anymore. You will have only virtual one. That's not true, because native thread still makes a lot of sense, and virtual thread is a tool, one more tool in your toolbox that you learn how and when you may want to use them. Okay, so I explained you the main feature of virtual thread, but they also come with some issue, some theoretical, some more really more. A lot more practical. One of these issue is that, as I said, with virtual thread, the stack of virtual threads is actually another object on the heap, okay? So this is an object on the heap, and typically, a stack grows and shrinks quite frequently, quite fast, and it means that with virtual thread, you are simply giving more work to do to the garbage collector. Okay, that's the thing. It is unavoidable. It's one more set of objects that the garbage collector needs to take care of. And if you have really millions of virtual threads, this may be a problem. I also discussed this with Ron Pressler at the latest Devox, and he made me notice, yes, true. Still, this is only half of the truth. The second part of the story is instead that if you think about it, each and every native thread is a root of the garbage collector. So if you have 1,000 native thread, you have 1,003 under the control of the garbage collector, okay? While virtual threads are not like that, they are not root of garbage collector. So if you have 1,000 virtual thread run by 8 carrier, you also only have 8 root of the garbage collector, not 1,000. So this plays at the advantage of virtual thread, of course, okay? Another thing that you really need to know and make to pay attention is that everything I said about a blocking call is true, meaning that a blocking call can remove the virtual thread from its carrier and give space to another virtual thread to do its job, unless the virtual thread is pinned. Okay, when a virtual thread is pinned to its native thread, to its carrier, even if there is a blocking call, that blocking call is not only blocking the virtual thread, but it's also blocking its carrier, which is something that, of course, you don't want. And when this happens, in a few cases, it happens mostly where inside a synchronized block. So if you have a blocking call inside a synchronized block, in that synchronized block, the virtual thread is pinned to the native thread. So if it performs a blocking call inside the synchronized block, it cannot be descoped from its carrier, okay? Meaning that in that situation, again, it is blocking not only the virtual thread, but it's also blocking its carrier, and that carrier is not available for other virtual threads. So the main use case again is for with synchronized block. There are other situations like GenAI function, native call function, where again the virtual thread is pinned to this carrier, and I explain what this means. Another thing is that with many virtual thread, what could happen is that you have a lot more of context switch, which is not a big problem like for native thread, because again the context switch is in the user space. But what may happen is that okay, you have a virtual thread running on a carrier that is running on a core of your CPU, and then, as I said, the virtual thread performs a blocking operation, and when it does, it goes to sleep, and then when the blocking operation terminates, it's waking up, but typically can be waken up on a different carrier. This carrier typically will live on a different, will run on a different core of your machine, and this means that you will have an L1 and L2 cache misses. So the heap of the virtual thread will need to be recovered from the L3 of the cache, and so you have a cache miss, quite huge cache miss if the stack of the virtual thread that lives on the heap, is big. And this could be another performance problem. Okay, and this problem is even bigger because at the moment it is not possible to plug your own scheduler. So far I spoke about this carrier thread. What are these carrier threads in reality? At the moment, this is hard coded in the virtual machine, and you cannot do anything about it. The carrier thread are a special instance of the fork join pool. So there is a fork join pool typically with the same number of carrier thread of the core of your machine. So on this machine, we'll have a carrier thread made of eight threads. And if you know how the fork join pool works, the fork join pool is based on the idea of work stealing. Okay, so if a carrier thread is not doing much, it can steal job from another thread. In this context, stealing job meaning allocating a virtual thread on a different carrier thread, and this can make the problem of cache misses even harder. One thing that we are doing, starting doing this day, is speaking with the people of the OpenJDK, because we would like to have an SPI through which we may want to plug our own scheduler. But again, this is not available at the moment. This is not possible at the moment. Okay. Another thing that is important is that virtual threads are not preemptive. What does it mean? It means that yes, when they performs a blocking operation, they are removed from its carrier and give space to other virtual thread to run. But the problem is what happens if they never call a blocking operation. The fact is that they are never descoped from the carrier, okay? So they are not preemptive. And this could be a problem, especially if you want a fairness in your application. Let me give you a very small and stupid example. So I created this task which is intended to be a CPU-bound task. As you can see, it just counts from 0 to 10 millions, and it does this accumulating the result on a big integer. Again, just to make the CPU to do more work. That's all. It's just a CPU-bound task. And then what I do is I execute this task 8 times multiplied by the number of core on my machine, which are also 8. So I'm executing this task 64 times on this machine. And I can do it in two ways, with native thread or with virtual thread. What happens here is that when I say, okay, run this thing on virtual thread, it just starts a new virtual thread. Otherwise, it takes a native thread from this pool. So the two other things that you need to notice here is that I'm using a thread pool for native thread, of course. It doesn't make any sense to use a thread pool for virtual threads because they are super lightweight, so you don't need to pull them. You are really wasting memory to pull them. It's not really useful. Okay. And the other thing is that I created this executor, and for native thread, I'm saying that the native thread are daemon, meaning that they cannot keep the Java virtual machine alive if they are the only one that are alive on the JVM. You also don't need to do this for virtual threads because they are daemon by default. Okay, so in essence, I run this thing in parallel 64 times with native thread in this first run, and let's see what happens. Okay, okay, take a few seconds. And yeah, the fastest thread takes around a little more than 2000 milliseconds, 2 seconds. And the slowest one took a bit more than 3 seconds, and in average they took 2.8 seconds. So yeah, maybe just remember this last number, which is interesting. Now we can do exactly the same exercise. Yeah, I think that I didn't make you notice. Okay, there is some variance, but more or less the duration is equally distributed among all threads, right? Now, let's try to make this exactly same exercise with virtual threads, and you will see the effect of non-preemptiveness in virtual threads. So as I said, my machine has 8 core. So what happens here is that the first 8 thread do something till here without giving space to the other because it's not preemptive. So the first 8 take the CPU, they take the 8 carrier, they do this job till the end without giving space to the other, okay? And then you have the other 8, there's another block with the other 8 and so on and so forth, right? So this is what I mean when I say it's not preemptive. So in this case, the fastest one took only 0.4 seconds. The slowest one more than 3 seconds because it has to wait all the other to terminate, okay? And what is also interesting in my opinion is that, okay, with virtual thread you lose fairness, yes, but it's interesting to also see, in my opinion, the cost of fairness, because if you remember, the average time took when I ran this with native thread was 2.8 second, and now it's 1.9. Okay, why? Because I'm not doing any context switch. I'm not doing any thread switch, and the context switch has a cost. Fairness has a cost. Okay, so if you are not interested in fairness but only on throughput, probably this could be a good solution. Okay, but you are losing fairness. So again, it's a tool with pros and cons, and it's important that you know them. The last thing is that virtual thread works with thread locals. The problem is that with thread locals makes sense with native thread when you have just a few threads, but you use thread local with native thread, you will have a thread for local for each thread. And once again, if you have 1 million virtual thread, you have 1 million instances of the thread local object for each and every virtual thread, and this could fill your memory. Okay, there is a JEP for this, the 429, that will change a little bit the semantic of thread local to work nicely with virtual thread. Okay, so this is the first part when I just wanted to introduce to you the virtual thread, how they work, and the pros and cons. Now there is the second part, meaning that, as I said, I wanted to play a bit with virtual thread to, do some code to get familiar with them, because you get familiar with the tool, with the pros and cons, with how it works, only when you really play with them. Okay, so I was looking for a nice way to put virtual thread that works, and then I bumped into this project on GitHub, made by a friend who lives in California. What he did is implemented the Conway's game of life. Do you know it? The game of life? Yes, I guess you do. With a concurrent technique that is called communicating sequential processes. So what is CFP? Okay, it's a relatively complex way of doing concurrent programming. If you go on Wikipedia, there is a formal definition. There is also a formal algebra to describe how these processes communicating between them and what they can do and what they cannot. But in reality, in essence, what CSP is a concurrent programming model where the communication is the only synchronization primitive. So between two threads, there is a channel, and these two threads talk through this channel. So a thread say, okay, I'm done, now it's your turn. And the other thread is waiting on the channel, say, okay, I got your message, now we are blocked, I can go forward. Okay, so all the synchronization is made just through messaging. And this means that this is the very essential primitive to make this programming model to work is a communication channel. Here the communication channel has been modeled with a blocking queue. So you have this channel between two threads where a thread is writing on the queue and the other is reading on the same queue. Okay, so this is our channel, how my friend modeled the channel, and then a cell in the game of Loom is a virtual thread. So the nice thing of this idea, and the reason why it puts Loom at work is that each and every cell that can be 1,000, each and every cell of the board of the game of Loom are its own virtual thread, and they communicate through each other through this channel. And if, as you saw, this is a blocking channel, so every communication is a blocking operation. Okay, so this leverages the good feature of virtual thread of as I said, be nice while waiting. Okay, so what how the cell is made? A cell is mostly a collection of channels. There is a list of channels through which the cell talk to the neighbor to say its own state, and there is another list of channels through which the cell read the state of the neighbor to calculate its own at the next iteration. And then there is another channel when the coordinator gives a tick signal to say, okay, this is now the moment to calculate the next frame. And then there is another channel when the coordinator read the result, meaning read the liveness of that shell. Okay, so what a cell does, they run in an infinite loop. And again, each and every cell is a thread, is a virtual thread. So what it does is waiting for the synchronization message from the coordinator, from the tick channel. Then it reads the liveness of all the neighbor. It calculates its own state. It communicates the new state to the neighbor, and then communicates the state to the coordinator. And okay, the algorithm to calculate the state is the usual game of life algorithm where a cell is alive if it was alive before and there are at least 2 or 3 neighbors alive, or if there are 3 neighbors alive. And what the coordinator does is that it sends a tick message to all the cell, and then it waits for the result for all the cells. So it collects the liveness of all the cell, and then it sends this result to the user interface, so the user interface can enlight the cell that are alive. Okay, so yeah, just to show you how it works. Yes, I played a bit with this project. There are now a lot of way you can customize it, but basically it's the game of life that you are used to. So what's happening here is, again, each and every cell is a virtual thread and is communicated with the neighbor and with the coordinator through those blocking queue, through those channels. Okay, that's all. So I started with this project, but I forked it. But I really want to put it to work, and I really wanted to compare how this works compared to the native thread. Okay, so what I did is I changed it quite a lot, this project. I introduced a few degree of freedom, and I put this degree of all this degree of freedom at work with a JMH benchmark. So what I did is allowing to use either native or virtual thread, is allowing to having 1 thread per cell as the original implementation, or grouping the cell in different, or having a number of thread equal to the number of core on my machine and group the cell by thread. And then what was very interesting is that I tried with different implementation of that channel type, not only with the original blocking queue. And I tried this thing with a few different dimension of the board. So I tried with a board with a padding of 5, meaning that I had a little less than 1,000 cell. And then I made another attempt with like 5,000 cell, and another one with 50,000 cell. Okay, and yeah, and what this thing is doing, of course, this is when I benchmark this, of course, this is running headless. So what it does is counting how many frame per second I can do. Okay, so instead of giving the frame to the user interface, is giving to the frame to JMH to say, okay, I did 1 frame, I did 1 frame, I did 1 frame, and the score of JMH is checking how many frame per second you can do, and the more are the better, of course. Okay, so I made this first run comparing native and virtual thread. And as you can see, both with 1000 cell and 5000 cell, the virtual thread were around 7 times faster. Okay, and of course I couldn't run the the biggest board with native thread because simply I cannot launch 50,000 native threads on my machine, so it went out of memory. Okay, so then I tried to figure out. Okay, so yes, virtual thread are really performing a lot better in this case, but why? Okay, so I try to do some flame graph of this different execution. Who knows how to read a flame graph? Okay, very few. That's why I added this slide. So what a flame graph is that it gives you a visual way to figure out where the time is spent in your virtual machine execution. So these flames that you see are different stacks. Okay, on the x-axis there is not a really order. They are just ordered alphabetically. What is important is how large a bar is, because the more it's larger, the more time it is consuming on that call. And the other interesting thing are the colors. So the green cells are the normal Java call. The aqua, the light blue one, are the inline Java call. The orange one are the call that happens in the kernel space, typically context switch of native threads, as I said. And the red one are C libraries. So, for instance, when you do an invocation through Java native interface, and the yellow one is C++ code. So, typically, when you see yellow stuff, it's garbage collector doing its stuff. Okay, so I try to compare these two execution, generating the flame graph. This is the flame graph of the native execution. Of course, here you see 5,000 flames. 5,000 graph is not very readable. What's interesting here is that in purple there is the call of the coordinator. There is the call of the thread that is reading that is running JMH, let's say, that is running the coordinator. Okay, and if you zoom on a single native thread, you will see a lot of those orange stuff, meaning that it's doing a lot of context switch and it's losing lots of time in that thing. Okay, and comparing this with virtual thread execution is quite interesting. Now you see I have 8 flame. Why I have 8 flame? Because this tool samples the native thread. So I have 8 carrier thread, which are the native thread. This is one interesting thing. And the other interesting thing, if you see now, the also the JMH invocation, also the coordinator, it's not only on one single thread, but because of the fork of the work stealing algorithm of the fork join pool, you see that the work of the coordinator is spread among all carriers. Okay, and the other nice thing that you see, of course, is that you don't see any orange operation here. You don't see anything happening in the kernel space here. Okay, so I ran this thing also with a switch that allow me to count the context switch specifically, and in a typical operation, if you see the difference, you have like 10 context switches for virtual thread. You have 15,000 context switch for native thread, which is really where they are wasting time. Okay, so this makes sense of the result that I got. This makes sense of that 7 plus speed, 7 per speed. Another experiment that I did is trying with different different channel implementation. Okay, so as I said, the original implementation used a blocking queue, but then I realized that you really don't need a queue in this application. It's just one value at time that is read from a side, that is written from a side and read from the other side, from the other thread. You don't really need a queue. Okay, so I created this abstraction that I called blocking rendezvous, and I created the 4 different implementation of this blocking rendezvous. One is backed by the blocking queue, another is backed by another non-blocking data structure available on the JVM that is called the blocking transfer, which is a little better because again it uses well, it's blocking, but it uses a lock-free algorithm. And then I created 2 more abstraction. One is, okay, I figured out I don't need a blocking transfer queue or a blocking queue. I don't need the queue at all. It's just one single value that has to, at time, that has to be passed from a thread to another. Okay, so I created an abstraction that just allows to carry one single value and coordinate the thread. Okay, and then I went so far, and I made this thing, I shared this thing with a colleague of mine whose name is Francesco Nigro. So if you like crazy tweet, you can probably follow me. But if you are really into Java performances, you should really follow this guy. And the other thing that Francesco noticed is that there is one more constraint that we can leverage. It is not only true that I need only one value instead of a whole queue, but one more constraint is that it's always the same thread reading, and it's always the same thread writing on this thing. Okay, so when I create a channel, I create a monodirectional channel between 2 threads. There is one thread only always writing, the same thread always writing one value at a time, the same thread always reading that value. Okay, and leveraging this further constraint, he created this data structure that coordinates specifically those 2 threads, not 2 random threads, but those 2 threads. Okay, so I put these 4 different implementation at work again with a benchmark. For native thread, as you can see, the result didn't change much, but this is just because we already know that the bottleneck is somewhere else. We already know that the bottleneck is in the context, the massive number of context switch in the kernel space made by native thread. But if we give a look to what happens with virtual thread, you see the blocking queue, you see things a little better with the blocking transfer, you see things are still a little better with my data structure that only carries one value at a time. But the data structure made by my colleague Francesco, it's super fast. It's more than 2.5 times faster than the original implementation. Okay, so the bottom line here is that yes, virtual threads are nice, but the domain knowledge of your domain is even more nicer, and you should leverage it. You should keep your brain on. Okay. Okay, and yeah, you can see what's going on here. The put operation on a channel takes like 1,900 sampling with the original block and queue, and just a third of them with the Francesco data structure. So that's why this is much faster. Okay. Okay, I will go fast here. There is another attempt where I grouped the thread per core instead that per cell, and of course by doing this you are playing more on the native thread grounds, and in this case the native threads go fast. But yeah, we can wrap this up so with a few conclusion. So in essence, virtual threads aren't faster thread, aren't magic, aren't something magic that allows you to make your CPU run faster. What they are really good for is waiting, unless they are not pinning. So beware of pinning. So in other words, they are a way to maximize the utilization of your resources. And I have exactly the same goal of reactive programming, but in a much more readable way. So they are really good for IO-bound operation. I showed you the problem with non-preemptiveness. So they could be good in some situation with CPU-bound operation as well, but you need to be aware of the problem. And again, they are not drop-in replacement for native thread. They are two different things, two different tools, and you know to know both to know where to put them at work in the right context. And yeah, once again, let me reinforce this. The domain knowledge still matters a lot. So keep your brain off trying to understand the constraint of your software and where you can really make a difference in performance by fine-tuning that stuff. Okay, and I left you a few references here. There are a few articles. If you are interested in the special data structure created by my friend Francesco in reality, there is a blog post by Martin Thompson explaining how it works. There is some word about the red-blue function problem. That is the reason why we want a transparent blocking operation instead of doing what, for instance, Kotlin does. A few very interesting blogs made by my friend Simone Bordet, the maintainer of Jetty, with his experiment in the context of the Jetty web server that I guess you know. And that's all. Thanks. Sorry, I didn't have time for question, but I'm around, so please feel free to stop me somewhere.